Alright, so we're going to talk about the graphs of our trigonometric functions. I'm going to presume you've done the things you need to do. You've read through the section, maybe you even reviewed your function translations and function transformations from um, your college algebra course. So we're going to go through some of these notes. If you haven't looked over that stuff, do make sure you're looking over that stuff before we go through the notes. I want you to have the time to be able to do that. So we've seen where these functions come from. One of the distinctions I like to try to make really solid is this distinction between the unit circle here. This unit circle is the graph of x squared plus y squared equals 1, and it's a tool we use to define our trigonometric functions, but isn't the graph of our trigonometric functions. The graph of our trigonometric functions are these curves. So the unit circle is a tool, but it's not the graph of our functions. But it's the tool from which we can grab the values and plot them out. And you can see as we go around the circle, we create this first oscillation, and if we continued to go along that circle, that first oscillation would continue in its natural sinusoidal pattern in both directions. And you've seen from your reading that cosine looks very similar. You can see from the blue line, it's the x values, and we've talked about that before. You can see it's a very similar curve to sine, just offset a bit. And that should seem to more natural now as you've seen building the unit circle. The x and y coordinates are just switching. Sine and cosine are really the same basic argument, just at slightly different angles. And if we wanted to look at them all together, we could look at what tangent looks like and what secant looks like. You can even see the lengths here. This is a similar argument to the one that I went through in one of the other videos with the tangent length and the secant length. It's the same triangle there, it's just kind of flipped. We could even add cosecant and cotangent and look at everything happening at the same time. That's always a little overwhelming, but I don't know, it's also kind of cool. But we will look at them a little more individually. Also in your reading, you've seen the connection between like cosine and secant, the way that they are, the fact that they're reciprocals of each other create these arcs being flipped on themselves. So we'll talk a little bit more about that relationship. Same thing happens with sine and its reciprocal, cosecant. So when we talk about graphing cosecant, we won't really be talking about graphing cosecant all that much. To graph cosecant, we just graph the sine function. The asymptotes live where we cross this midline. Wherever you cross the midline, you're getting a zero whose reciprocal is undefined, so you get that asymptote. And then you flip these arcs over to make cosecant. So as soon as we learn to do cosine and sine, we can do secant and cosecant. Tangent is a little bit different. It still has those kind of asymptotes, but its behavior is a little bit different. Also, it repeats itself in a smaller period. That should be in your reading as well. Instead of having to go all the way from 0 to 2 pi to repeat itself, it repeats itself after just 1 pi. So you can see this whole big sweep lives in a range of 1 pi. We'll tend to think of it as this sweep and the part in the negative part of quadrant 4, but it's all still, it all happens within pi radians as opposed to 2 pi radians, which is going to come up every now and again. And the cotangent is still highly related, so it still has that kind of flipped relationship. So we'll still essentially graph cotangent based on tangent, but it'll be a little different than secant and cosecant. So again, make sure you're looking over this material beforehand. We're going to go through it fairly quickly in the notes. I want to make sure you get a nice kind of robust idea of some of these notes. So on your notes, you're listing, they list one period as being from 0 to 2 pi, but keep in mind that that period is from any location to the repeat of that location. So you could measure the period from max to max, from min to min, even from like this location on the way up to the next instance of that same location on the way up. So that amount of distance or time or whatever your input variable is, that amount of that input variable is one period. And you'll often see period symbolized or denoted with a capital T. I presume it's from the Latin, but I'm not sure. But from sound and electronics, sometimes you'll see it as a T, so I'll use that notation sometimes. So our natural period for sine and cosine is 2 pi. It does have a domain of all real numbers. It does keep going in both directions. Tangent, secant, cosecant, cotangent don't have a period of all reals. They have those undefined locations in them where the asymptotes are. But sine and cosine are comparatively well behaved and have full domains. Sine and cosine, we've talked a little bit about, have this restricted range. If you remember your circular definitions, particularly your unit circle definitions, since we're defining our trigonometric values based on the xy coordinates as we go around the circle, it should be fairly clear that the maximum y value is positive 1, because this dot's never going to get above positive 1 or below negative 1, and same with cosine, it's stuck between negative 1 and positive 1. So unmodified, our sine and cosine values will always be trapped in that range. Again, tangent doesn't have that restriction. Tangent can become infinite. Secant and cosecant, similarly. Actually, secant and cosecant can't exist inside the range from negative 1 to positive 1, unmodified. They can only exist outside because they're reciprocals. And again, cotangent, like tangent, has a range of all reals, but has the domain restrictions. And we'll talk more about those restrictions and how we deal with those restrictions when we talk about inverse functions. That's often a little bit of a complicated discussion, and we'll refer back to these graphs individually when we talk about those. Being an odd and even function, it does come up quite a bit, particularly as you get into some of the calculus work, taking advantage of the fact that sine and cosine, and actually all the trigonometric functions, are either even or odd. But if you need to review that, go look up odd and even functions, but the short version is that sine is odd, so is tangent, frankly, because one side, left and right, looks like the other side. It's just when you flip around the y-axis, your graph flips around the x-axis. So this positive part becomes that negative part. So they have the same structure, a symmetric structure. It's just that symmetric structure is reflected, we say, around the origin, because it flips both around the y and the x. Cosine, again, it has the same shape, but unmodified. It's an even function because left and right, or positive and negative x, it's just a mirror of itself. We often refer to both of these functions, the sine function and the cosine function, as sinusoidal functions, because really, again, cosine and sine are the same argument, just different places, different parts of the rotation. So really, anytime you're modeling something with a sine function, it could be a cosine model that's just modified, or any cosine model can just be a sine model that's modified. So often you'll see us choose whether to use cosine or sine, depending on whether we want to consider our function to be starting at a maximum or minimum, versus whether we want to think about our function starting at its center line. So if we want to start at the center line, we'll think in terms of sine. If we want to start at mins or maxes, we'll think in terms of cosine, and then modify the functions from there. So the things that we will look at as we modify these functions are primarily these four pieces. We're going to look at coefficients out in front, coefficients being multiplied by the trig functions, constant terms being added after the functions or outside the functions, and then coefficients and terms happening inside the functions. So those four values are going to determine the change in behavior from our standard sine. Cosine is going to be the same for tangent, cotangent, secant, and cosecant as well. Looking at those four things and what they do. And again, I know you've read through this. Feel free to go back and stop this and go back and read through some of that stuff if it helps. But this a out in front, that multiple out in front, it's going to take those values between 0 and 1 that are coming out of the sine and multiply them by that a value. So in this example down here, that sine function generally only goes up 1 and down 1, but since it's being, in this case clearly that a would be 3, multiplying by 3, is going to push those values, instead of going from the center line up 1, they're going to go from the center line up 3, and from the center line down 3. So whatever this function is, it does kind of look like our sine curve, but it's going to have a 3 out in front of it, because that nice 3 is going to make those peaks higher and those valleys lower. And if this was a sound wave, that amplitude really would determine the loudness of the sound. The period affects its frequency, the amplitude, its loudness. So it really, our association with the word amplitude really is appropriate. You notice the amplitude's always positive. It is an absolute value because it is the distance from the midline up and down. If the value in our function had been, or in our coefficient had been negative, our amplitude would still be 3. It would just, instead of starting off increasing, starting off going upward, it would just start off going downward instead. So it just causes that vertical reflection, again, that you should be used to from your function translations. As I said, this number on the outside, that d, it's going to determine our midline. It's going to take these function values, whatever they are, and just add a constant amount to it. So instead of occurring at 0, since this midline is up at positive 1, we're going to be taking whatever our function is and just adding 1 to all of those values. It's just pushing everything up by 1 unit, changes where our midline is. So essentially, I like to think of our sinusoidal function will be centered along this value and be trapped up and down by that value. So we're centering at 1 and then going up and down by 3 for this particular case. Now, we don't have a phase shift in this one. We'll talk about phase shifts more very, very shortly. But the reason I say it doesn't have a phase shift is because you might notice it is starting on that y-axis like we think it should. Now, usually the sine function starts at 0 at the midline. So there's no phase shift being caused, and this constant inside is what causes that phase shift to occur. So we don't have a C value in this particular one, and that's nice. It's always handy. The phase shift's kind of the harder one to work with. But since our period is not standard, our period isn't our standard 2 pi, we do have some b value that's affecting our period. So since normally our period would be 2 pi, this value out in front, the coefficient of the variable inside your function, is going to cause a compression factor. It's going to cause the function to happen faster. So that 2 pi divided by your compression factor is going to give you your period. Now, I call this a compression factor by habit. A lot of people like to think of it as a speed factor. So, for example, in this one, we'll talk about how we know in a second, but in this particular example, it's 3 sine 2x. So what that 2 is doing is it is compressing, it is shortening the function, but you can think of it as speeding the function up. So instead of the function going a full oscillation between 0 and 2 pi, this 2 is essentially doubling its speed, so it's going to go through its oscillation instead, terrible, but it's okay, from 0 to pi. And that's why we're dividing. We're taking that 2 pi and dividing by that speed factor, because it's happening faster, so it's going to happen faster. So given that this period here was pi, we can find that b by just letting our period be pi equals 2 pi divided by b, and solve for that b. That b would clearly have to be 2. That's how we knew that was a 2. If you have the b and need to find the period, take 2 pi and divide by whatever that coefficient of the variable is in your function. Now, this doesn't have a phase shift, but if it did, the important thing about the phase shift, or the two important things about the phase shift, notice that there is this negative here. You remember from your function transformations that everything happening to the independent variable, everything happening inside the argument for that function, is going to be happening backwards. So if this is a subtraction, that's actually going to push us in the positive x direction. Just like this multiple of 2 didn't make us twice as long, it made us half as long. So be sure not to forget that from your function transformation logic. And one of the things that makes phase shift a little bit more complicated is the fact that the phase shift essentially happens before this compression, so it has to be compensated for. And that's why our phase shift is always going to be this constant, but then compressed by the b value. So say we had the sine of, I don't know, how about 5x plus 10? Well, that plus 10 kind of wants the function to go this way 10 units, so we might think to start there and go through our sinusoidal function. But that 10 unit shift is then going to be compressed by 5 and turn into a 2 unit shift, and then oscillate from there. So be a little cautious about that. This number here isn't by itself our phase shift, our horizontal shift left and right. This constant divided by our compression makes how much we're actually shifting. And if you want to, I wouldn't necessarily get in this habit, but it's you'll see it done sometimes. Some textbooks like to do it. Some people like to do it, and it's a totally fine thing to do. Just a thing to be careful of. If you think of this with that 5 factored out, that 2 is your phase shift. So if we separate it out, we can see that 2 in the equation. Generally, we do it by dividing it out kind of outside the function, but if you wanted to factor it within the function, you can. Just make sure you don't do both. So, given a particular function down here, one of the things you tend to want to do is identify all those pieces using your A, B, C, and D, essentially. So, again, our amplitude is the absolute value of that A value. Our A here is -3, so the absolute value of -3 is +3. The negative does mean that we will start going downward instead of upward from wherever our phase shift is if we were to graph this, but that doesn't change the fact that the amplitude is that strictly +3. Our period for sine and cosine and cosecant and secant, our natural period is 2 pi. That period will be divided by our B, our compression factor, in this case 4, which will give us a period of pi/2. That phase shift, we kind of want that phase shift to just be 1. Remember, it is +1 because it is the opposite of that sign. Everything's going backwards. But remember that phase shift, that C value, has to be compressed by that period change before it actually becomes our phase shift. So our phase shift there is going to be 1/4. And then our midline is going to be the line y equals, or d y equals pi. So that's really all you were asked to do, is list out the period, amplitude, and midline. You didn't even have to do the phase shift on that one. We did anyway. But even if you're asked to graph it, writing those 4 things out first is really handy. Not only does it get you used to thinking through your parts, but also if you have trouble with graphing it properly, but somebody can see, okay, you have the right pieces, your drawing is just off, that can help you get more credit for that. But if we want to sketch just the roughest of graphs, we'll sketch some nicer graphs later. Our midline is at y equals pi, so at pi we're going to have a midline. We're going to go up and down from that midline 3, so pi plus 3 is a little more than 6, so pi plus 3, and down 3, so pi minus 3 is almost 0, but not quite. And then our phase shift of +1/4, so +1/4, so we'll go over 1/4. And then our period is pi/2, and pi/2 is about 1.57, so that plus pi/2, I'm going to kind of arbitrarily draw it over here, so, but that's pi/2 plus 1/4. And then our function's going to sit between those 2 locations. Because our original coefficient was negative, instead of starting upward, we are going to start downward. Do be careful about that. And it's going to go through an oscillation between those 2 points. It'll hit the midline again halfway through. It'll reach its minimum in this case at 1/4 of the way through, and its maximum at 3/4 of the way through. So once we know these values, we can sketch out a graph. We also need to be able to go from a graph to an equation, at least an idea of the equation, depending on how precise our graph is. And we don't always need all of the pieces, particularly for this matching kind of tool. Like figuring out exactly what the phase shift is, and particularly this third one, we could do, but it can be kind of a pain. So, start with the nice pieces. Excuse me. This thing has a maximum of 1 and a minimum of 0. So the center line has to be halfway between that. We could even say, 0 plus 1 divided by 2 is 1/2. So the center line has to be at 1/2. So we already know that's our D. So if we wanted to, we could just then look down and go, do any of these have a D of 1/2? And that one has a D of 1/2, so that has to be D. But if we wanted to kind of keep going with that, the distance from that midline up and that midline down, each of those are 1/2 upward and 1/2 downward. So that gives us an amplitude of 1/2, and this is our center line at y equals 1/2. Huber calls it midline. I say center line a lot. Sorry. Let's see, we're going from 0 to 2 pi as we go through a full oscillation, so it looks like our period is just the standard 2 pi, so I wouldn't expect a compression factor. Usually, I said cosine, we start at the maximums and minimums, so the fact that this is cosine makes sense. But normally we think of cosine as starting at its maximum and going down. This starts at its minimum and goes up, so it's got a negative in front of it. So that's got all the pieces this thing needs. But really, as soon as we knew that 1/2, it had to be A. But we can figure out all the rest of it from the graph as we need to. This second one here, again, our center line's at 2. So our center line is y equals 2. So our lift value, our D value, had better be 2. It goes up 1 to 3, down 1 to 1. So our amplitude is 1. We can start at that nice center line and do one oscillation, so I would expect it to use sine without a phase shift. It does go upward, so I'd expect this lead coefficient to be positive. Our period is 2 pi, so I wouldn't expect a compression factor. That center line is occurring right on that y-axis, so I wouldn't expect a phase shift. So amplitude of 1 you often don't see, so that's a little amplitude of 1. Lift 2, no compression factor, no phase shift. That's got to be C. This last one's got a little bit more going on, and it's a little bit hard to read, but it does go from a maximum of 1 to a minimum of -5. So our amplitude has to be our max minus our min divided by 2. So how far do we go up and down from our center line? So 1 minus -5 divided by 2. You want to do it that way. So 6 divided by 2 is 3. pen to be thinner. So we're going up 3 and down 3 for amplitude. So we'll be looking for something with a coefficient out in front of a 3. That means our center line has to be down 3 or up 3 from any of the extremes. So 1, 1, 2, 3. So that center line has to be happening at that -2, which we probably could have picked out anyway, but if it's hard to see, just go from your max to your min and calculate it. It's often handy, particularly if the graph's a little imprecise. So y equals -2 is our center line, so we have a d of -2. And whether or not this is a sine graph or a cosine graph is a choice. It depends on like who built it and what they wanted. It's either a cosine graph that starts here and goes downward with this little positive phase shift, or it could be a sine graph that starts from here and goes up with this even tinier phase shift, depending on how somebody wanted to write it. Either one is perfectly fine. If we want to determine its period, it looks like it goes from 1 there out to 7. So it looks like the period is equal to 6. And we know period should be 2 pi divided by that compression factor, the coefficient of the x on the inside. So if that's 6, that's got to be 2 pi divided by b, multiply by b divided by 6, so b is 2 pi over 6, so b is pi over 3. And we could calculate what the c value has to be. We might as well. Like we know over here somewhere you can look and see, okay, what has these pieces in it. But if all we had was the graph, I'd probably use a cosine, because this is a nicer value. It looks like it's at +1. I don't know where that one is. Could be about a half, but I don't know. So let's grab this phase shift of +1 and figure out what that c value would have to be. Because right now we've got 3 times the cosine of our compression factor, the pi over 3x, and then there's going to be some c value for our phase shift, and then -2 for our midline. We got to figure out what that c is, and remember that c isn't the amount of the phase shift, because that phase shift is that c value divided by the compression factor. So we always have to make sure we take that into account in one of a couple ways. But this is one of the nicer ways. So if our phase shift was 1, we want to find that c. We know our b is pi over 3, so multiply both sides by pi over 3, and we'll get pi over 3 equals c. So pi over 3. So hopefully one of the things down here says that, and oh cool, that one does. So given a graph, if we can figure out a couple of points on it, and generally we look for maximums and minimums because they stand out, but maximums and minimums are centers, we can determine amplitude, lift, phase shift, compression factor, all of it, and come up with what our equation has to be. And there are a lot of applications in modeling where we do that. We do exactly that. So let's see. In this next example, again, we're not asked to graph the whole thing yet at this point, but we're determining the direction and magnitude of the phase shift. Oh, that's cool. Okay. Phase shift does tend to be the complicated part. So magnitude and direction of the phase shift. So phase shift is always left or right and a particular distance. So the left and right is going to be determined by primarily whether that's a positive or a negative. And again, remember your function translations, everything inside is always backwards. So the fact that this is a positive means this thing is going to go in the negative direction. So this is going to shift towards the left or towards the negative side. I know that always seems weird, but there's a reason for it. The graph isn't shifting, the actual number line, the axes are shifting in the positive direction, which makes the graph look like it goes in the negative direction. So there's reasons for it, but really it's important for us to not forget that, because if we do, things will go wrong. And by how much is the phase shift going in that direction? Well, that, again, we like to think it's just this number, pi over 6, I would say, in the negative direction. But we do have to remember to divide by any compression factor we might have, but in this case that compression factor is just a 1, so our phase shift would be negative pi over 6. So what direction? Left. What magnitude? Magnitude is a raw value of how far. So the magnitude we'd say is positive pi over 6. The saying the phase shift is negative pi over 6 kind of combines those two pieces of information. How far? Pi over 6. In what direction? In the negative direction, so to the left. So, you know, the phase shift goes pi over 6 units to the left. Fine response. And just to be, you know, complete about these things, its center line would be at y equals -2, would be the midline. If we were asked that, its period, the standard period for sine would be 2 pi, but divided by a compression factor, but there is none. Well, it's a 1, so its period is going to be 2 pi. And its amplitude is just going to be 1, because there's 1 in front of that. And given all that, we could graph it. That makes me want to graph it. So at -2, amplitude of 1, so that's at -2. So our amplitude of 1 means we go from -1 to -3, so our function's going to be trapped in between there. We start at pi over 6, so we're going to start at pi over 6, but it went to the left, so it's over here. Negative pi over 6. Almost forgot my own phase shift. And then it's going to have a period of 2 pi, so it's going to end at 11 pi over 6, because if we take negative pi over 6 and add 2 pi, we're going to get 11 pi over 6, and that was a positive 1, so we go upward to begin, so we're going to live in that nice range. And if we wanted to figure out where, we'll talk about this more in a little bit, but if we wanted to figure out where those maxes, center, and mins were, well, they break the graph into quarters. So the distance between each one of these is a quarter of the period. So a quarter of 2 pi is pi over 2, so that's going to be pi over 2, that's going to be pi over 2, that's going to be pi over 2, and that's going to be pi over 2. So we could calculate each of those points, and we will later on. But I'm overdoing this question. This question just asked for the magnitude and direction of the phase shift, so that's it. Graphing sinusoidal functions. Oh, how to. So, determine midline amplitude and period. Yep. Divide the length of one period into 4 subintervals. That's what I was doing down here. Take that period. Yeah. Okay. Take that period and divide it by 4. And again, in this case, it was 2 pi divided by 4. So pi over 2. And that's going to be how far between each of your values. Find those 5 key points. The start, max, min, middle, and end, in whatever order they occur. And then using the midline amplitude, plot 5 key points and obtain the graph. So that's how we graph functions. Do we have some nice graphing examples? Oh, come on. Don't start arguing with me. Did I zoom in too far to make you unhappy? Sometimes I have to let the computer catch up with me. Okay, there we go. Sorry about that. So, sketch the graph. So again, the first thing that I want to do is find what's our amplitude, what's our period, what's our phase shift, if any, and where is our midline. So, amplitude is the absolute value of that A coefficient. So in this case, it's going to be positive 4. I will remind myself that it's negative by making a little downward arrow. Just, yeah, it's positive 4 is the amplitude, but remembering that it's going to be in the negative orientation is helpful. Our period is going to be our standard period, 2 pi, divided by our little compression factor or compression coefficient or speed factor, however you want to conceptualize it. So divided by pi, those are going to cancel. So it gives a period of 2. We're not adding or subtracting another term in there, so there's no phase shift. And our midline is at that D value, so the midline is at y equals negative 2. And once we have those pieces, we can draw a graph. It is nice, the advice you had down there is to look at those quarters. To figure out where those 5 key points are. So those quarters, we take our period and divide by 4. So that's going to be 2 divided by 4, or 1/2. So each of our pieces are going to be split up by 1/2. So our start is going to be at our phase shift value, which is going to be 0. Then our first, either max or min, since we're doing sine, or our first, I don't even want to specify max or min, it's going to change depending on whether we're doing sine or cosine or cosecant, but our start is going to be at our phase shift 0. Then our first quarter point is going to be 0 plus our quarter distance, 1/2. So that's going to be at 1/2. That's our first quarter point. Then our second quarter point is going to be another 1/2 out. So 0 plus 2 1/2 if you want, or at 1. Our third quarter point is going to be at our starting value plus 3 of our quarter distances. Oops. Or 2 or 3/2. And then our fourth quarter point is going to be at our phase shift plus 4 of our quarter distances, or 2. Oftentimes this start is called our 0th quarter point. So sometimes you'll see, x0, x1, x2, x3, x4 for those quarter values. And the reason that these are handy is when we go to graph it, I know I could graph it down there, but we know we're going to have a midline at -2. Okay, so if I want that midline at -2, our amplitude is 4, so we're going up 4 to +2 and down 4. Yeah, it's going to start getting into an ugly graph. If your graphs start getting ugly, redraw them. No matter how noisy it might be. So at -2, that's our midline. Then we're going to go amplitude of 4, so up 4 to +2, down 4 to -6, and our function is going to oscillate between those two lines, centered at -2. And then here we have our quarter points. So our critical points, our points of interest, are going to happen at 0. And notice I'm plotting them on our midline, but that's from the 0 up there on the x-axis. 1/2. So 1/2. 1. So we're going to pass. So something's going to happen at that point. 3/2. And 4/2, or 2. So we're going to start there, we're going to end there, and now we know where all of our pieces are, remembering to start off downward. So downward, then upward. That's one period of this function. So if somebody asks, what's this point down here? Well, we know its x value is 1/2, and we know its y value is 6. This point has an x value of 1, a y value of -2 on our midline. X value of 3/2, that's these x values. Y value 2, because that's on our maximums, our amplitude above our center line. And this one's at 2, -2. So that's, and of course this one at 0, -2. So those are our 5 defining points for one oscillation. The only thing that would be different is if we had a phase shift, is that whatever that phase shift is would replace those zeros, and we'd start a little bit left or right. And if we wanted to graph an extra period, we know our period is, what was our period? Our period was 2. So if we go back, say, this direction to -2, we can put another oscillation in there. And we could do the same to figure out what all those points are. 1/2 unit, 1/4 value is going to move between each one of those. I know it's weird having the quarter value be 1/2, but you'll get used to that. Let's see. Yep, that's the last one, that one. Okay. So, got cosine this time, that's good. Determine the amplitude period And phase shift, this one has a mid-value change too, so we'll do all of them. So our amplitude is 3, but it does have a negative orientation. So the amplitude is just 3, but I like to remind myself about the negative orientation. Our period, our natural period for sine and cosine, 2 pi, divided by our compression factor, 2. So our period is going to be 1 pi. Our phase shift is going to be this constant, which, remember, is negative pi. Remember, your form says bx minus c, so this has to be a negative pi for that to be plus. But just also remember your direction's backwards, so it's going to be going in the negative direction to the left. But also, don't forget to divide by that compression factor. So our phase shift is going to be negative pi over 2. And then our midline is going to be at y equals 1. So our 0th quarter point, or our starting value, is always just the phase shift, which was pi over 2. And then we're going to add quarter periods. So our period this time was pi, so our quarter periods are going to be a fourth of that, pi over 4. So our quarter periods are going to be pi over 4. So at first, we're just going to be at our phase shift, then our first quarter point, our phase shift, plus our quarter period, then our phase shift plus 2 quarters, then our phase shift plus 3 quarters. These quarters are actually quarters, that's weird. And then our last quarter point is going to be at our phase shift plus all 4 quarters. Now, you don't necessarily have to be this formal about it, but the nice thing about being this formal about it is your points will be in the right place. If you have a different way of thinking through it, that's absolutely fine, but some way of organizing yourself is really, really handy. And that's so we can graph it. So we're essentially on to number 2 at that point. We already have our amplitude, we already have our period, we already have our phase shift, and we added the lift or the midline because we want to be able to graph it. Okay, so I just want a little more space than that gives me. So our midline at y equals 1, I'm always going to start there. And then our amplitude of 3, so we're going to go from 1 up 3 to 4, and down 3 to negative 2. And I just like to do that because it gives me a little window. Our curve is going to live inside of that range. And then, what our scale is, we could put, 1, 2, 3, 4, 5, 6, and then figure out where pi over 2 is. Remember, pi over 2 is about 1.57, so if we put, 1 and 2, negative pi over 2 would live between negative 1 and negative 2 if we wanted to. But since we're dealing with, pi over 2 and pi over 4s, we might as well make our scale the same way. So I'm going to scale this just in terms of pi over 4s. So that's 1 pi over 4 negative 2 pi over 4s, negative 3 pi over 4s, and so on. Negative 4 pi over 4s, which would just be negative pi. I don't know how many of these I'll need or want. Negative 5 pi over 4, and so on. And 0 pi over 4, pi over 2, 3 pi over 4. And this is where getting that, constructing the unit circle down helps too. We're doing the same counting as we did around the unit circle. We're just doing it along the x-axis now. So we're going to be starting at negative pi over 2, so it's going to start here. Its period is pi, so we're going to go a full pi out. That's 1/4, 2/4, 3/4, 4/4. So we're going to end there with a quarter of a pi in between. Now you could actually do the math on these, there's nothing wrong with that at all. So that's going to be at pi over 4. That's going to be, mathy that out. That's going to be at, what's it going to be at? It's going to be about pi over 4. Oh, sorry. That's negative at pi over 4. And then that's going to be at 0. And that's going to be at pi over 4. And that's going to be at pi over 2. So if you add those together, and it's good to check that because we are starting at pi over negative pi over 2, and when we added a period we ended up at positive pi over 2, so that is where we ended, so good. So then at pi over 4, negative pi over 4 is going to be one of our quarters, so 0 is one of our quarters, and pi over 4 is one of our quarters. Now to know exactly where to start, that's going to depend on whether we're sine or cosine. This is cosine, so remember, standard cosine starts at its maximum and then goes through an oscillation. But because of that negative, we're actually going to be starting at the bottom and going upward. So we're going to be starting down here at our minimum, then go through our midline at our first quarter, then our minimum at our second quarter, midline at our third quarter, minimum at our end. So our single oscillation has to live right there. And again, we could draw another one, which would be out at 3 pi over 2. So it would have to live in there. And often it'll be asked to graph 1 or 2, depending on what you're being asked. So again, these can be really handy to just calculate formally so you can plot them. It takes practice, so make sure you're getting that practice in. But the nice thing is, the only difference if this was sine would be that instead of starting at the minimum, we'd be starting at the center and going downward, as opposed to starting at the minimum. All of the other logic of where the quarter points are and amplitude and phase shift, all those arguments are exactly the same. And even better than that, when we switch to cosecant and secant, we get to use all of the same logic, because we're really going to graph secant and cosecant by first graphing the corresponding cosine and sine. Because you can see, and again from your reading, that if we know where the graph crossed those midlines, again by finding those quarter points, that's where our asymptotes are going to be. And then we can take each of the kind of the arcs and flip those arcs upside down to get our curves. And again, that's happening because of the reciprocal. You're talking about numbers, again, remember, that are between 1 and negative 1, so numbers are less than 1. So when we take their reciprocal, we get large numbers, like 1/10, its reciprocal's 10. 1/100th, its reciprocal's 100. So these get to be very large values in secant and cosecant. But all of our logic is really the same. We still have, what's going to be an amplitude and a midline and a compression value. A period is still the standard period for sine and cosine, and then divided by that period shift or that compression factor. And yeah, the vertical asymptotes creating this little formula for the vertical asymptotes, and you could use this formula if you wanted to compute them, but you already know how to compute where it crosses the midline, so you don't necessarily need a new formula for it for secant and cosecant. Just draw your sine and cosine. Where they cross the midline, that's when the function was 0. Those are where the asymptotes occur. So you don't have to get as complicated as this is kind of almost encouraging you to think you have to be. All we really need to be able to do, as our next example kind of illustrates, is if we can say we want to graph this secant, you essentially don't graph the secant. You go and graph the cosine and then perform the transformation. So, since this is what the cosine looked like, again, it's going from -1 to +3, so 1, 2, and 1, 2. So our midline is happening at 1. And again, we can see that our midline is happening at 1. So any place where we're crossing that midline, we're going to get vertical asymptotes. Anywhere we cross that midline, we get vertical asymptotes. And so on and so on. Then, once we have those, where's our graph going to live? Well, the only reciprocals that equal themselves are 1. The reciprocal of 1 is still 1. And this might not look like it's happening at 1. It looks like it's happening at 3. But that 3 is because of this 2 and that 1 combining to make the 3. The cosine, at that maximum, the cosine is outputting a +1, whose reciprocal is still a +1 times 2 is 2 plus 1 is 3. So those minimums and maximums are all where the function itself is creating, where the trigonometric function itself is creating its positive and negative ones. So those are on both graphs, and then the reciprocal just takes over and creates our little sweeps. That one didn't want to curve. So, I often say secant and cosecant, they're not that hard to graph because we don't graph them, really. We do, we just did. But we graph sine and cosine and then just make the asymptotes and flip them. And then you've got your graph for secant. Oops. Here we're asked to determine what's the period and what's the vertical asymptotes, and we could use that formula, but you probably get the sense by now that I'm not going to. Our period, well, I would again first conceptualize this as 3 cosine pi over 4x minus 2. Those aren't the same function, but we're going to use cosine to understand secant. our natural period for cosine is 2 pi, but we had to divide by that compression factor, pi over 4, multiply by 4 over pi, and get a nice period of 8. So we got a period of 8. I'm not really concerned about the amplitude and the midline because we're not asked about those, but we certainly could draw them if we wanted to. But we know there's no phase shift, so we know this thing's going to start at 0 and has a period of 8, which means if we divide it into its quarters, our quarter periods, oops, I did that backwards, our quarter periods are length 2, so at 2, 4, and 6. And this is a cosine graph, so we're going to start at the top, go to the bottom, so we're going to cross through there, bottom out, cross through there, reach our maximum. So where we cross that midline is where we're going to get asymptotes. So again, what was our period? Our period was 8. Where are our vertical asymptotes? Where the first vertical asymptote happens at 2. And then if you add not 1/4 but 2 quarters, so in this case 2 quarters would be 4, you keep adding multiples of 4 and you'll get all of the rest of them. So 2 and 6 and 10 and 14 and 18 and so forth. Go the other direction, -2, -6, -10, the other way. For k an integer, and that's going to be where all of your vertical asymptotes are. And I guess if I was going to try to be a tad bit more formal than that, your vertical asymptotes are the equations x equals those. So the vertical lines being x equals 2, x equals 6, x equals 10, and so forth. So we can get there just by knowing what our cosine graph looks like. And that is really the same thing, that's going on up here. It's the same kind of k, and it's the same, this is odd integers because it's doing the half quarter, and it's one relationship for cosine, one relationship for sine, because sine, where the midline is and starts, is different than cosine. So you could keep all those complications in your head, or draw the graph of the cosine, draw the graph of the sine, and look at where those middle lines happen. Domain and range, again, those kind of sound like complicated questions, but remember, your domains are your inputs, and range are your outputs. We often think of them as our x's and y's, but only if those are the variables involved. If your inputs are thetas, then your domain is your theta values. So better to think of them as inputs and outputs than x and y's, but in this case they are x's and y's. So if we want to know what the domain and range are, again, I'm not going to think about cosecant. I'm going to think about sine and based on knowing what that looks like, determine what our domain range has to be, as opposed to trying to keep track of all those formulas and which case you're in and all that. Because we already know that our midline is going to be at, for sine, our midline is going to be at 3. Our amplitude is 1, so we're going to go as high as 4 and as low as 2. Then catch up. And really, we know our sine will be trapped in between those. So our cosecant, the reciprocal, will be outside of those, will be above and below. So even just from that, even just from looking at, there's my midline, my amplitude is 1, we know the range already. The range, it's going to go from negative infinity to 2, and from 4 to positive infinity. Our output values are going to be below 2 and above 4. That's where our graph is going to live. So that's our range. To find our domain, we've got to figure out where those asymptotes are. So we got to go a little further, but our period, our natural period for sine is 2 pi divided by that compression factor, 2. So our period is going to be pi. And our phase shift is going to be that positive pi over 2, but divided by our compression factor of 2. So pi over 4. So our graph is going to start at our phase shift, pi over 4, and then we're going to add quarter periods. So pi over 4 plus a quarter of our period is another pi over 4. And then add 2 quarter periods. Then add 3 quarter periods. And then add the last quarter period. Again, you don't always have to be this formal, but it's really helpful. So we're going to start at pi over 4, and we could even, put a little graph there. We're going to start at pi over 4. And that's, again, because this is sine, we're going to start on our midline, so our asymptote's going to occur there. And then we're going to reach our maximum at pi over 4 plus pi over 4 is pi over 2. And then add another pi over 4, we'll get to 3 pi over 4. 4 pi over 4, which is of course pi. That delay is bugging me. And then add another pi over 4 is 5 pi over 4. So which ones of those are going to be middle lines? Well, again, this is why your section talks about odd integers or even integers, because our midlines for sine are going to happen at 0, 2, and 4, the even numbers. They're not really even, but it's okay. And for cosine, it happened at the odd ones. But I don't want to have to remember all that. We already know or have to remember how to graph sine and cosine. So just do that and use that to figure out where everything has to be. So one of those asymptotes is going to be at pi over 4. Pi over 2 is going to be a max, so not a problem. And then the next midline is going to happen at 3 pi over 4. And then you're going to have a minimum down there at pi, and then back to the center line at 5 pi over 4. So our asymptotes our asymptote. So our domain it's going to go, it's going to try to go from negative infinity to positive infinity, but it's going to have a hole in it every, well, 2 periods. 2 periods is pi over 2 in this case, so it's going to go from, how do I want to write that? I want to go from pi over 4, like one of them is going to go from pi over 4 to 3 pi over 4. And then there's going to be a hole in it, and then it's going to start over at 3 pi over 4 to the next one was 5 pi over 4, and then from 5 pi over 4 to 7 pi over 4, and we could keep writing that, and you can see the odd numbers that it's talking about. And of course it's going to go in the other direction as well, from pi over 4 to negative pi over 4. But it would be nice to have a handy way to write that, and your text suggests that when it talks about writing your domains here, so all real numbers except where those asymptotes are. So really the best way to write that, oops, that's not what I wanted. Oh, I just moved that. Sorry. So really the best way to write this domain is that the domain is all real numbers except pi over 4 plus k times pi over 2. And that's what we're doing. We're going from pi over 4 and then add 2 of our quarters to get to 3 pi over 4, and then add 2 of our quarters to get to the next one. So k times 2 quarters. So all reals except those. But your set builder notation, x an element of the reals where x is not equal to your text likes the k times pi over 4 where k is an odd integer or an even integer. And again, you could do that, but just saying that it's this anchor point plus some multiple of 2 of our quarter periods, just to be more explicit there. And yeah, I'd perform this multiplication to clean it up, where k is an integer, is totally fine. So write it in language, write it, this is about the only bad way to write it because you have to write that forever, but you can still actually even write that in a similar fashion to these. So however you want to end up writing that out, check with me if you have any concerns about that. So now it's saying graph the whole thing using a reciprocal function. That's just kind of a hint to, again, don't graph secant. Graph y equals 2 cosine 1/2 x plus 1 instead, and then flip it. Our logic is not going to change. Our amplitude is 2. Our period is going to be our standard 2 pi over our compression factor, 1/2. So that's going to be 4 pi. Our phase shift is 0 because there's nothing being added there, and our midline is going to be at y equals 1. Come on, thank you. So that's what we're going to graph, and then we're going to turn it into the secant that we actually want. And I'm actually going to make this a little bit of a light gray, so it looks like this isn't what we're actually graphing, it's just the model that we're using. So, but our midline is at 1. And you don't have to draw that dotted line that I keep drawing. I just like it because it, I'm not using graph paper, but also just, keeps me knowing where I am. Amplitude of 2 means we're going up 2, so that's going to happen at 3. So that's where our max is going to be. And then down 2 to -1, so that's where our minimum is going to be. And our graph's going to live in there. No phase shift, luckily. Awesome, no phase shift. And then our period is 4 pi, so we're going from 0 to wherever we decide we want 4 pi. I want 4 pi to be there. How do I know 4 pi is there? Because that's where I wrote 4 pi. And yeah, 4 pi is 12, almost 13, but I'm going to list it in terms of pi's because it's easier. And then if we wanted 8 pi is there, and so on and so forth. Our quarter periods are really nice because our period is 4 pi, so our quarter periods are just 1 pi. So we're going to have something fun happening at 0, because that's where we start, no phase shift. And then at 1 pi, something's going to happen. At 2 pi, we're going to be in our middle, and then at 3 pi, we're going to be almost done, and at 4 pi, we're going to be all the way done. That's a terrible drawing, but that's okay. Changes everything when I zoom in. I want more space. Never be afraid to change your drawing. So 4 pi. So our quarter points are going to be 0, 1 pi, 2 pi, 3 pi, and 4 pi. We're doing cosine, so we're starting at our maximum, then going through our midpoint, then our minimum, then our midpoint, then our maximum. And so at negative pi, if we wanted, at negative pi, we'd be going through our midpoint again. At negative 2 pi, we'd be going through our maximum, and then or our minimum. Then at negative 3 pi, we'd be back to our midline, negative 4 pi. We'd be back to our maximum. So particularly for secant and cosecant, graphing 2 periods is always nice. But notice that tells us where our asymptotes have to be. So our asymptotes have to be wherever we hit that center line. So we're going to have an asymptote at 3 pi. Sorry, that's all fuzzy. We're going to have an asymptote at pi. We're going to have an asymptote at negative pi. We're going to have an asymptote at negative 3 pi. Not one in the middle. I drew that earlier. Now, one of the tough things is we haven't graphed secant yet. We have a nice graph of cosine, but we haven't actually graphed secant yet, other than that we know now where the asymptotes are. But when we go to graph our actual secant function, we know we have to be asymptotic at our asymptotes, and we know we're going to match up at all those maxes and mins. So just go to those maxes and mins and flip the graph upside. And that purple is the graph of 2 secant 1/2 x plus 1. And then if you want, you can go in and erase the cosine so nobody knows how you did it. And they'll go, how did you graph that so beautifully? And you'll be like, well, I studied hard, did a lot of work. I did the reading, that's why. Heck, you can even erase all this other stuff and go, I'm just that good. And people will have no idea how you get such beautiful graphs. I get a better graphics card. So, graphing secant and cosecant, as long as you know how to graph sine and cosine and know how to perform the flip, it's not a problem. That does, by the way, make secant and cosecant very popular questions for exams. Because if I want to know that you know how to graph sine, I can ask you a cosecant question. You have to graph sine, and then you have to know how to do the flip. So it's almost like 2 questions in one. Tangent and cotangent are a little different, as you can see. The major difference is that the basic period isn't 2 pi anymore. The basic period for both tangent and cotangent is pi. And you can see that happen. It goes through that one wave, that one oscillation between negative pi over 2 and pi over 2 in 1 pi. And you remember from your unit circle, tangent goes through its positive values in quadrant 1, then its negative values in quadrant 2, and then starts over again with its positive values in quadrant 3 and its negative values again in quadrant 4. So it really goes through all of its values in that first half rotation. So we could consider its period to go from, say, this center up, and then from here to that center. That's like our first quadrant and our second quadrant from our circle. But that's kind of irritating to have it broken up into pieces that way. So we kind of consider, we actually consider its main period to exist between those asymptotes at pi over 2 and negative pi over 2, which will come up a lot in our section on inverses. So we still get that same b being our compression factor, so we're still going to divide by that b to figure out our period, but our standard period, our natural period, is only pi, not 2 pi, when we're dealing with tangent and cotangent. You'll notice the amplitude doesn't really come up down here. We don't care much about the amplitude. Our amplitude, since we don't go to a max and a min, our amplitude really doesn't affect all that much. Technically, our amplitude, like say this was a 5, would mean at pi over 4, instead of being at 1, we'd be at 5. But all it does is change how steep this curve is. So it really doesn't change the structure all that much. So we really don't tend to care much about this amplitude, which in some ways is nice. It gives us less to do when we're dealing with tangent. We do care about where these asymptotes are. We do care about where that lift is, where that midline is, because if our midline was, say, up here instead, go ahead, load that up. If our midline was up here at 2 1/3, it is going to make our graph exist up here instead. So where that midline is important. But unless you're doing some fairly specific types of applications, which some of you will go do, and it'll be okay. We really don't care about where that mid is happening, where those quarter periods are happening, because they're just not as significant as the mins and the maxes. And then again, for cotangent, just like secant and cosecant, if we can graph the tangent, then our midlines become our asymptotes, and then our curves flip. They flip a little differently, but but we'll talk about that once we draw it. So really, we care a lot more about graphing tangent, and if we have to graph a cotangent like we do down here, we'll just flip the thing. So determine the period and vertical asymptotes of this cotangent. Well, again, really, we do find period the same way. We take our natural period and divide by the compression factor. The difference is our natural period is now pi divided by that compression factor. So we'll have a period there of 2. And again, for tangent, I'm going to think of tangent first and then think of its reciprocal. Tangent centers at the origin, and then its period is divided on both sides of that origin. So tangent, if that period is 2, then this is going to be at 1, and that's going to be at -1. So tangent would have asymptotes at 1 and -1, and then the next one would be 2 away at 3, and then 2 away at 5, and so on. And again, you can see the odd integers. The only difference going from that to cotangent is our midpoints become our asymptotes, and our asymptotes become our midpoints. So cotangent would have an asymptote at that midpoint, an asymptote at that midpoint, and so on. Catch it. So where those midpoints are become our asymptotes, and our asymptotes become our new midpoints, and these things flip upside down. Just like secant and cosecant. Well, a lot like secant and cosecant. So where would the vertical asymptotes be? The vertical asymptotes in this case would, for cotangent, would be at 0, 2, 4, would be at x equals 0, 2, 4, and so on in both directions. And again, how you want to write that, they'd be at x equals, I would say, 0 plus plus iterations of our period, so 2k, and really I think that's a nice way to do it. And that's what they did too. So, again, really, once we know how to graph tangent, we know how to graph cotangent. And frankly, to be honest with you, you won't graph cotangent a lot. People don't use cotangent very often. They just use tangent. I mean, it does happen sometimes, but not terribly often. So, if we want the equation of this thing, we really want two things. We want our period, and we want to know if we have any kind of lift. So our period is going to be that distance there. Yeah, the longer these run, the slower they get. So that's going to go from -4 to +4, so that distance is 8 units. So that means our period is equal to 8. And our period for tangent is its natural period, which is again pi, over our compression factor. So we want that to be 8. So solve that for b, multiply by b, divide by 8. B is equal to pi over 8. So that's our compression factor. It doesn't look like there's a lift. We're not really worried about amplitude, so we're going to assume our amplitude is 1 unless somebody tells us we have to care about our amplitude, which I'm not. So y equals our tangent of pi over 8x, because there's not even a phase shift. So that's it. Some nice application problems. We'll talk a little bit here about what that amplitude does if we want it. It's going to be a long video, but we're going to do all of them here, so that's nice. So a nice application question here. Give you a chance to read through that real quick. Just give it a pause and read through it real quick. So a nice classic tangent question. So nice of it to allow us to ignore the curvature of the Earth. So if we've got, you know, a nice rocket being launched over here, and that's 2 miles away from some camera location. As the rocket launches, the camera is supposed to track it as it increases in height. It's hard to draw that when the screen's not showing it. Okay. And this angle, which we're going to call theta for a second, that angle is going to be pi over 120x, because that angle is going to increase over time. Every second that goes by, that angle is going to increase by pi over 120. So we know that the tangent of our angle, we know the tangent of our angle should equal our opposite over adjacent if you want, so our h over 2. So our height is going to be 2 times our tangent of our angle, but our angle is that pi over 120x. So that's what we're asked to graph. So, you know, we do have an amplitude of 2. I'm not so concerned about amplitudes right now. But we have a period here that is our natural period. And again, our natural period for tangent is pi, divided by this compression factor, pi over 120. So the pi's cancel, multiplied by your reciprocal, 120. So that's our period. So if we were going to graph this, our period of 120 would be split on either side of our starting point. So our asymptotes are going to be at 60 and negative 60, though we were only asked to graph from 0 to 60, so we really only care about this part over here. And our curve, so our graph is going to go like that, and up this way, and we really only care about this part. So we really only care about this part of our graph. Okay, evaluate and interpret our h of 0 and our h of 30. Well, h of 0, plug a 0 into this, tangent of, pi over 2. Making a video.
Little babies, they come with trash cans.
Sorry about that. So if we imagine putting in that 0, pi over 120 times 0 is 0, tangent of 0 is 0, so times 2 is still 0. So h of 0 is 0. Well, at time equals 0, x is time, how high is this rocket? Well, it hasn't gone anywhere yet. So at 0, we get 0. Okay, so rocket's on the ground. That's our interpretation. Rocket on ground. I'd write that out, but it would take forever for the video card to figure it out. At 30, okay, plug in 30. 30 and the 120 would cancel, so we'd have pi over 4, tangent of pi over 4 is 1, 2 times 1 is 2, so 2, and it would be miles, because that was miles. So after 30 seconds, how high is this thing? Well, after 30 seconds, it's 2 miles high. So it is 2 miles high after 30 seconds. But what about this asymptote? What's happening with this asymptote? Well, again, remember our variable, our x is time, but it's creating this angle. So if you were this, camera person, at first this angle's going to increase pretty fast, but as this rocket gets higher and higher, well, notice your angle's never really gonna get to 90 degrees. But if you can imagine you're standing there, your head's just as the rocket gets higher and higher and higher, your head is going to get tilted and tilted and tilted more upward as this rocket gets higher and higher and higher and higher. But at no point is that angle ever going to get more than 90 degrees, and that's this asymptotic effect occurring. So as we get close to that 60-second mark, we're looking up essentially infinitely high. So in context of the problem, as we approach 60 seconds, the rocket is flying off out of view as we start trying to look straight up. So we're looking straight up or trying to almost straight up as this thing launches up and up and up. And again, I'd like to write that out, but my video card's starting to crash. So I'd love to graph this one, but I think I have to make a whole nother video for it because I think I'm crashing here. But again, our logic is going to be exactly the same as it's been for all the rest of these. We have a midline at 1, so your midline is going to happen at that y equals 1. Our period is going to be our standard pi divided by our compression factor, which in this case is 2. So we're going to have a period of pi over 2. Again, that's going to be on either side of that center. So that means our asymptotes are going to be at pi over 4 and negative pi over 4. That's the one thing to be careful of. Make sure you're dividing that period on either side of your center. It's very easy to forget to do that. And then that period, that amplitude, again, I'm not going to worry too much about that. If you wanted to, you know this is at 1, and then so at half of that, at pi over 8, you'd be up 3 at 4 and down 3 at negative 2. So if you wanted to figure out where those quarter points are, you're certainly welcome to. It's a nice and interesting thing. But since we don't start and stop there, it really doesn't end up being a point we worry about too much. So sketch or graph a tangent. And if it was cotangent, do the same thing we did up there. Our midlines become our asymptotes. Our asymptotes become our midlines, and the thing flips upside down. I'm going to have to start breaking these into smaller pieces. I think that's what's causing the problem. I think it's storing it all in my RAM, and after an hour and 47 minutes, it doesn't have any RAM left on my video card. So we'll fix that. But if that gives you any trouble, let me know. Do make sure you're doing your reading and working on some problems and going through these notes before we watch these videos together. It's really to kind of go through everything one last time. I'm going to remind you of that periodically. But try to have fun with it. And if something comes up that you need, please let us know. Thank you. Have a beautiful day.